This resource is the first of a three-part series that looks at systems of equations. Part 1 defines systems of equations. It then considers the meaning of a solution to that system of equations. It looks at three examples, one of which is a word problem. Part 2 presents the substitution method of solving systems of equations. Systems of two variables are presented, as are special cases for systems of three variables. Part 3 looks at the elimination method for solving systems of equations. Systems of two variables are solved in full. We will also look at elimination for systems of three variables, but in interest of time and attention span, only the beginning steps are shown. A system of equations happens when you have more than one variable. In the comic, the variables are the costs of a sweater and of a shirt. To successfully solve a system of equations, you must have as many equations as you have variables. So you would need 3 equations to solve for 3 variables, or 20 equations to solve for 20 variables. Systems of equations are often needed to model more realistic situations. Think about flying a plane. To find the optimal cruising height, you would need to factor in the wind speed, the weight of the aircraft, the weather conditions, and many other variables. Another common situation, modeled by systems of equations, would be mixture problems, an example of which is presented later. We see two systems of equations. The first example shows a system of two equations in two unknowns. The second example is a system of three equations in three unknowns. We also see an example of a mixture problem, as the speaker has a mixture of quarters, dimes, and nickels that meet certain criteria. Our job as mathematicians is to solve these systems. But what exactly does it mean to solve a system of equations? A solution to a system of equations means you find values for all variables that work for all the equations. When you plug each of those values into each equation and work through, you end up with a true statement. It is important when checking solutions to plug into all equations. Sometimes a potential solution works for one equation, but not for the others. A system of equations may have one solution, or there may be infinite solutions. It is also possible that a system has no solution. This situation is called inconsistent solution. Let's see how we check a set of values to verify that we have indeed found the solution for a system. If we consider the first example from earlier, it turns out that the solution is x equals 5 and y equals 14. At least, we think that is the solution. To make sure the answer is correct, we need to plug into both the original equations. The first equation was 2x plus 3y equals 52. When we plug in our potential solution, we have 2 times 5 plus 3 times 14, which we hope is 52. Doing the multiplication, we have 10 plus 42, which we persist in hoping is 52. And we get 52 equals 52. All right, the solution works in the first equation. Now we have to check the other equation. We have 7 times x minus 2 times y equals 7. Plugging in, we now have 7 times 5 minus 2 times 14, which may hopefully equal 7. Multiplying, we get 35 minus 28 equals 7, we hope. And 7 equals 7. Since the values worked in both equations, we did indeed have the correct answer. What if we have a system of 3 equations in 3 unknowns? The second example was just such a system. We worked through the problem, and we think our answer is x equals 9, y equals 4, and z equals 3. To check, we have to plug into all three original equations. The first equation is 2x plus 3y minus z equals 27. Plugging in, we have 2 times 9 plus 3 times 4 minus 3, which hopefully is 27. Multiplying out, we get 18 plus 12 minus 3, which may just equal 27. And it does. So the solution works for the first equation. Now let's try the second equation. We have 5 times x minus 4 times y plus 2 times z equals 35. Plugging in, 5 times 9 minus 4 times 4 plus 2 times 3, which we posit is 35. Multiplying gives us 45 minus 16 plus 6, hopefully to be 35. And this works too. Now for the last equation. This equation looks like 6 times x plus 11 times y plus 3 times z is 107. Plugging in, 6 times 9 plus 11 times 4 plus 3 times 3 may just equal 107. Doing the multiplication, we have 54 plus 44 plus 9, hopefully to equal 107. And it does. Since the solution checked out for all three equations, our job here is done. The word problem gives a whole extra layer of difficulty. First, we have to figure out exactly what our system would look like. Since we have quarters, dimes, and nickels, we will let Q represent the number of quarters, D the number of dimes, and N the number of nickels. The first equation we can form is that Q plus D plus N equals 9, since we have a total of 9 coins. The next equation would be 25 times Q plus 10 times D plus 5 times N equals 115. This is because each quarter is worth 25 cents. So 25 times Q is the amount of money we have in quarters. Each dime is worth 10 cents, and nickels are worth 5 cents. The last equation is a little trickier. Since we have twice as many nickels as dimes, if we subtract 2 times D, the number of dimes, minus N, the number of nickels, we get 0. Now that our equations are set up, we can solve, and we find that we have 3 quarters, 2 dimes, and 4 nickels. But does this work? Let's check. First, we have Q plus D plus N equals 9. Plugging in, 3 plus 2 plus 4 is hopefully 9. It is. Now let's try the next equation. We have 25 times Q plus 10 times D plus 5 times N equals 115. Plugging in, we have 25 times 3 plus 10 times 2 plus 5 times 4, hopefully equaling 115. Multiplying, we get 75 plus 20 plus 20 may equal 115. Which it does. And now for the last equation. 2 times D minus N equals 0. Plugging in, 2 times 2 minus 4 should equal 0. 4 minus 4 should be 0. Which it does. But how do we actually find these solutions? There are 2 algebraic methods, substitution and elimination. We will explore each of these methods in parts 2 and 3 of this series, respectively. It is also possible to solve a system of equations graphically, but this is more difficult to get good answers. Your graphs must be perfectly precise, and I recommend sticking to the algebraic methods. So stay tuned, and we'll learn how to solve soon.